Thank you so much. So, pleasure to meet all of you and very good afternoon. I know that the flavor or the content of this talk is probably a little bit different from what you have been usually exposed to, but also it's kind of an opportunity, I think, to know each other better. And I'll try to give you some context on where this can be useful, given that there's a lot of focus on AI and data centers right now. I mean, people are talking about billion-dollar investments in these areas. And so if you think about it, people are also talking about putting up data centers in space, right? You have probably heard some of these, media bites from, I think, Elon and Jensen Huang, right? So in our group at IIT Tirupati, so we work in two research directions. So one is focused on timing systems, where we want to create these portable timing sensors for various applications, and the other is quantum communication, right? And so if you think about it, the sharing of information across any network is inherently dependent on the timing system. So, for example, my talk is getting beamed on the internet, right? And so there's basically a server clock somewhere, which is basically sort of feeding the data packets into the network. And so the audience at the other end of the network is able to deconstruct these data packets into meaningful audio and video signals. So PNT, positioning, navigation, and timing, is at the heart of everything we do, right? Our modern civilization would cease to exist if the PNT network, the architecture breaks down, right? And so it's extremely important, both from the civilian applications, like, for example, day-to-day ticket booking, or let's say we make a bank transfer or a phone pay transfer. Everything is connected to a timing network at the end of the day, right? So you do something on the stock market, that's again connected to time, right? And then, of course, there are very deep implications from strategic and space requirements as well, right? So, secure communication. For example, you want to create an entangled network, right? And so you want to distill entanglement within the network. That again, you need extreme, element of time synchronization within the quantum memories or the quantum repeater architecture. Right? So timing sensors is critical even for various quantum communication applications. So under the National Quantum Mission, we have our technical group, which is led by Professor Urvashi Sinha at the Raman Institute. So the group's mandate is to create a quantum repeater architecture, entanglement-based quantum repeater architecture. And so we have three experimental PIs, Professor Urvashi herself, myself from Tirupati, and Professor Raghavan from IIT Patna. And then we also have two distinguished theorists. One is Professor Aditi Sende from HRI and Professor Sandeep Gwal from Ahizan Mohali. So it's a very small, neat group, but then we are sort of trying to take our efforts to the next level, where my group is focusing on the development of one type of quantum memory. And then as a group, we have taken a conscious decision to create a hybrid architecture, which means that we'll have both solid state memory as well as atomic memory, which will be sort of integrated in a very nice way. And then this Professor Sandeep Gwal and Professor Aditi Sende, they are basically giving the theoretical backup to sort of implement all these experimental activities in a meaningful way. So today I will sort of dwell upon the timing essence of any kind of network or communication. And so we have been recently working towards creation of a portable optical atomic clock, which represents a paradigm shift in how clocks have been envisioned, right? So if you are aware that, let's say you want to move from one point of any place in Earth to another point, you take out your cell phone, you open Google Maps, right? And so what you do essentially is, at the end of the day, there is a GPS transmitter which connects to your local cell phone tower, and then it beams that signal to this constellation of satellites which are moving around the Earth, right? And each of these satellites have about 3 to 4 onboard atomic clocks, right? So the moment something is beamed up, it gets tracked by more than 3 or 4 satellites, and they sort of triangulate your position on the surface of the Earth. There's an algorithm which actually then tags it to your local latitude and longitude point. And all of this actually happens within less than a millisecond, right? So we don't even realize, right? It's almost happening in real time, except that there is a whole series of events that is happening at the back end, which we sort of are, oblivious to, right? So in some sense, we have been living in the quantum age since 1967, ever since the GPS, was open to the public domain. GPS was a US property at some point, and then they decided to open it up. And the whole concept of GPS is that there is satellites which are orbiting the Earth, and each of these satellites contain clocks. And so now, coming to 2026, you realize that there is a lot of things changing across the world. There's geopolitical tensions arising at different regions of the Earth. And so it's very essential that we sort of create our own ecosystem in case somebody decides to switch off access to a certain signal, right? This already happened during the Kargil War, right? So they denied access to GPS signals over certain territories, right? And so that was kind of the turning point from the Indian policymakers, the strategic thinkers, that, okay, there is a dire need to design something, and that is how the concept of NAVIC originated, right? As of now, NAVIC constellation has, I think, less than 3 satellites with active atomic clocks inside, right? So they launched about 7 or 8. Unfortunately, most of the clocks have failed, and so the NAVIC system is kind of now redundant. It's not working, right? So in order to make it work, you need at least 4 or 5 satellites, and now we are up to, I think, less than 3 potentially. And so, a week ago we went to Sriharikota on a visit. We sort of learned that yes, the ISRO community is actually actively working to augment more NAVIC satellites, and potentially this financial year, if things go the way they want, maybe about 7 or 8 satellites will be put into orbit, right? So this is kind of the perspective, and so I hope this gives you some flavor as to why what we are doing in our group is important, right? So from various perspectives, like for example, we started with the era of this this edge GPRS network in a cell phone. Then we moved to 2G, then 3G, and then 4G. Now people are hyping about 5G. The Department of Telecom has already released a 6G vision statement, where if you hunt in that 78-page document, there is somewhere mentioned that atomic clocks are important, right? So they do realize that this is important, except that I think some more push has to be put in from the policymakers' perspective to actively fund these activities in a larger way, right? So what we are doing in our group at IIT Tirupati is that we are potentially investigating platforms which can represent the next generation of atomic clocks. So the atomic clocks, as I will show you, they are basically, we are trying to measure a transition, right? It can be an optical transition, it can be a microwave transition. So conventional clocks that we see from different sources, especially the ones in the satellites, they are all microwave clocks. So microwave means in, let's say, tens of gigahertz range. And so there is a limitation in the quality factor, right? I think you are aware about quality factor. So quality factor is essentially telling you how good an oscillator is, right? And so if you think about it, I want better and better clocks, right? So we started with the grandfather clock. Then at some point we went into the mechanical quartz clock. Then we went into the quartz crystal clock. Right now we have atomic clocks. And so with every phase of this clock development, what has actually happened is we have been able to resolve time much better. And resolving time much better gives us access to a host of PNB applications in communication, navigation, banking, whatever you can think of. These things will not work seamlessly unless you have a network synchronized to an atomic clock. So what I will try and do is I will try to motivate you briefly on atomic-based quantum sensors, sort of give you a background on what the platform is, what we are trying to do. I will show some results that we have got, which are sort of new from, these are not reported earlier everywhere, so these are very preliminary interesting results. And then I will also develop on the future work that we intend to perform, right? So if you look at atomic clocks, right, they all start with this small miniature cell. So this is a micro vapor cell based out of MEMS technology. So MEMS stands for micro electromechanical systems. So this is at the heart of everything you do in terms of quantum sensing. So whether you want to build a magnetometer to sense magnetic field, you want to build a new electric field sensor to sense RF fields, whether you want to build an atomic clock, the story starts from this cell, right? So vapor cell is at the heart of all this technology. So as I can, just outline the potential applications. So in our group, we are mostly working towards these 2-photon optical clocks, and the other one is the direct optical clock that I'm going to talk about. Then, of course, a huge amount of activities happen in magnetometers. For example, right now, MRI machines, right? So MRI machines, how they work, basically, they look at the microscopic magnetic activities inside the cell and tissue and brain, and then you can do this imaging, reconstruct that image to understand what's going inside. Now, MRI is expensive, right? If you go for any MRI treatment, okay, it's almost $10,000, 10,000 rupees, test that, or maybe more. And the reason it's so expensive is because you use extremely cold environment, because they are superconducting magnets. You need to run high current. So one of the options people are thinking is that, can we actually build an array of magnetometers which can be wrapped around the affected area of the body? And then if the magnetometers are precise and sensitive enough, we could actually map out what's happening in that, right? So this is a very potential area of interest for biomedical application, right? And so then you have radioactive field sensors, inertial sensors, again, very important for stabilizing aircraft or ships or rockets, whatever you can think. So this is like, there's a whole gamut of activities you can do, right? An atomic sensor basically is a very simple architecture. You have some light source, you have some vapor, and there's a detector, right? As simple as that, right? So all the magic that we see essentially happens because of light-matter interaction. So depending on the nature of the atom and depending on how the light interacts with those atoms, you see a certain signal, and then you can use that signal to sort of decipher relevant information. That signal can tell you what's the magnetic field. That signal can tell you what's the absolute frequency. That signal can tell you what's the electric field within the sense, right? So in general, you want to excite some transition, right? And you want to measure this energy difference, right? So you have probably heard about NV centers, right? Which are like these artificial atoms, right? So you basically put an NV center in a microwave field, there is some splitting, and then you can pump radio frequency energy to see what is the strength of that split. And then you can then calibrate the magnetic field according to the RF power frequency you're putting. So you see that these vapor phase atoms are basically a versatile and powerful platform for various kinds of quantum sensing applications. And so the reason then you may ask is, okay, this is good, but then why should we focus on atom-based quantum sensors? Well, the idea is that you have extreme precision in the values of these energy levels. So these energy levels are sort of calculated theoretically with very high accuracy, right? And then you can have the dependence of external fields predicted with very high precision. So I can sort of monitor what an external magnetic field does to my light matter interaction. I can sort of monitor very precisely what an external electric field does to my light matter interaction. And so this gives us an indirect way to probe these external fields, right? And then finally, we can actually do measurements with very, very high signal to noise ratio. And that's a good thing, because if you want to make a device, right, you would ideally want something which actually works in the real world, because the real world is not in the lab. The real world is where you have heat and humidity and everything, right? So it's a very complex environment, right? And so you want a very good signal to noise ratio. And so the advantage is that these atomic vapor cells or these atomic sensors, quantum sensors, actually give you that. So the other advantage is that, if you take an atom from a given element, let's say in the periodic table, I think all of us are aware, there are various elements, right? You have probably heard about lanthanides, actinides, group 1 metal, group 2 element, all that. And so the advantage is that these atoms are all identical, okay? So if you take an isotope from a particular element in India and then you go to someplace else, it's virtually the same, right? It's no different. And then you can also, because of development in technology, you can actually do isotopic separation. For example, all of us know that in order to create nuclear material, you need these high-level centrifuges which actually do this isotopic separation, right? So we have the technology to actually create any kind of atomic sensor based on a particular isotope. And so if you look at interfacing, yes, this again has made a lot of technological improvements. So I can sort of create a physics package and then I can couple it to some electronics elements and then I can create a device. And so what you realize is that these interactions can be interpreted from first principles, right? So I can use my basic physics to understand what is happening to the quantum sensor in the presence of external perturbations, right? So I can apply my perturbation theory, first order, second order, depending on the strength of the interaction. And I can try to understand, okay, what is the nature, what is the magnitude of this interaction? And then, reorient the question and say, okay, can I now measure the strength of this perturbation and tell me, or tell the user, okay, how strong or how weak it is, right? So given this situation, what you realize is that there are various kinds of sensors: electric field, magnetic field, acceleration sensors, right? Rotation sensors, right? So these are coming from inertial navigation systems, right? So for example, when an aircraft is flying or when a ship is sailing, there's an inertial measurement unit, right? So these are these classical gyroscopes which help you stabilize the motion of the vessel, right? Whether you're flying, okay, whether you are sort of navigating in water, you have this inertial sensor, right? And so what we see here in this chart is sort of what is the mechanism of interrogation, whether it's microwave, optical, Rydberg, all these things. And typically what you realize is that the number, sorry, let me go back, the number of atoms, designed or required to create a sensor is very high. I think probably we're running out of battery on this. Anyway, so what you realize is that these sensors are going to sort of give you maximum fidelity or maximum sensitivity if we can put sufficient number of atoms, right? So to build the signal to noise ratio. So now, given that this is the landscape of quantum sensors, what we are doing is we are trying to build clocks, right? So what's a clock? Okay, a clock has three elements. One is oscillator, second is a frequency reference, and third is a counter, right? And this is true for all clocks, whether it's your grandfather's clock, whether it's the wristwatch, whether it's the atomic clock, they perform in the same three, triangle architecture, right? So there is an oscillator, right? So example, in the case of my grandfather clock, this would be the pendulum that is swinging up and down, right? In the case of an atom, okay, this oscillator is represented by the light source, right? So the laser that I'm using to excite the atom, that is my oscillator. The frequency reference was the atom, right? Is the atom. In my case, in the case of my grandfather clock, it could be some arbitrary reference. It could be the time when the sun rises, you could synchronize your clock on that basis, or it could be, some other external source. Right? So in the case of the atom, right, we are looking internally into the energy levels. And so we want to excite two specific energy levels and then use this as a frequency reference. And once this interrogation is done and I'm satisfied, I would like to then translate this to a measurable information. And that is what the counter is. Right? So in an atomic clock, what you see, there's this atomic reference, is the physics package. There's my oscillator, which is the laser. I shine the light on the atom. I get some signal, and then I sort of pull a part of this light into a comb, right? It's a frequency comb. So Professor John Hall and Professor Theodore Pench actually won the Nobel Prize for the optical frequency comb, I think in 2005, if I'm not mistaken. So what does this do? Okay, this is a very interesting piece of device. Okay, earlier, prior to the discovery of the frequency comb, there would be a whole host of electronics that would actually enable you to measure the optical signal and translate it into a usable measurement in the form of a counter. And this series of electronic lockings that you have to do, it would actually span physically, it would span this whole room. So what happened with the discovery of the invention of the frequency comb is that now you could actually use a mode lock laser, okay, and use the spacing, okay, of a mode lock laser to convert this optical frequency, okay, into a usable RF signal, right? So any clock that you buy commercially, okay, which is an atomic clock, it actually gives you a 1 PPS or a 1 megahertz or a 10 megahertz reference. So for example, if you set up a GPS antenna, I'm sure this institute has some GPS antenna. So if you look at the GPS antenna, you look at the server rack, there is a 1 PPS output or a 10 megahertz output from that GPS system. Right? So what it does is it allows you to convert this optical signal into a usable RF signal, right? So that people can actually use it for other applications. That is the job. So now, if you look at just to go back, if you look at the tools to do this, okay, the tools are, one can use ion trapping or some other kind of technique. I know atom trapping. One can use resonant light and frequency measurement, right? Or one can use an imaging system to create this clock. Okay, so what we are trying to do is we are trying to avoid all these things because these kind of complicate the technology landscape. Okay, if you want to make a device which is user friendly, you need to simplify how it works. Okay, and then only it becomes usable for different end users. So if you look at the whole gamut of activities that are supported by clocks, right, you can see power grid management, stock market, internet synchronization, comms, radars, sat-nav, inertial navigation, astronomy, VLBI stands for very long baseline interferometry. And so all of this is kind of being facilitated because of the PNT services the clock offers. Right? So in our case, as I mentioned, we are interested in creating the 2-photon clock, right? And right now, our interest is, if you look at the energy level diagram, this is for rubidium atom. So rubidium atom has, this is the ground state, right? And so you can excite the atom from this ground states to various other states. So you can do an excitation at 5p3 by 2, okay, 780.24. There is one more level which is sort of not shown here. This is at 5 to p half, that is at 795. Okay. But anyway, these two levels are not of interest to us. What we are interested in is in the 778.1. And so you can see that it doesn't connect to a direct energy level. It connects to some virtual state. And so this process, okay, connecting to the virtual state is a 2-photon process. And the atom then comes here. From here, there is a sort of branching ratio to different states. And so 30%, 33% of all the atoms that reach here, 33% of them decay to this state, which then comes down to the ground state once again. through this 420 nanometer transition. Right? So what we want to do is we want to see how we can use this transition to our advantage. Instead of going in a complicated process, can we directly excite on this transition itself and try and build a clock? That is what we are aiming to do, right? So what are the advantages? Advantages is that, if you look at the two-photon transition, you look at Doppler phase spectroscopy, it's a simple optical architecture. And then the only things that perturb this signal are collisional shifts, right? The disadvantages are that because you want to excite as many atoms as possible to this state, okay, you would need to put in a strong power of light. And so if you put a strong power of light, you also sort of get affected by AC stark shift, right? And then in that situation, you have this collisional shift which dominates, right? So all this typically are happening when you try to excite this two-photon transition. So right now, what we are trying to do is we are trying to see if instead of the two-photon transition, can we actually use this 420 10 nanometer transition, which is the classic decay channel for all experiments connected to the two-photon transition. Can we directly excite on this channel and make a usable clock out of this? That is what we are trying to see. And the best reported stability for this transition on the two-photon is at the level of 10 minus 13 with 1 second of average. So here's the full energy level diagram of rubidium. As you can see, you have the downstate, 5 2s right? And then you can excite to either 2p12, this is at 795, and you can also excite to 2p3/2, which is at 780. So I think most of us remember about the sodium D1, D2 lines, right? Sodium doublet, right? So this represents the D1, D2 line for rubidium. Okay, so in sodium, if you recall, the D1, D2 is at 5890 and 5896 angstrom, right? So if you convert that, it's like this yellowish light. So sodium vapor lamps are all yellowish light. Rubidium, on the other hand, is infrared, right? You can see the two D1, D2. So this is at D2 780 and D1 is at 795, right? So these are the two D1, D2 for the rubidium atom, right? And then one can excite from 5p to 4d, right? So what we are trying to do is, if I just go back one slide and want to show you, we are trying to sort of look at the 778 two-photon channel, but then instead of exciting directly on this channel, we are trying to excite it on the 420. So if you now go to the next page, hopefully we'll be able to see what we are trying to do. So we try to excite directly on this, but then the problem is once the atom reaches this state, it has this ability to choose which path it decays to, right? And so there is a 55% chance that it decays to this state. There's a 20% chance it decays to this state, and there's like a 2% chance it decays to that state, right? And so what we are saying is that what is the pathway of decay directly back to this state? It's only 23%. So let's say if you are able to excite 100 atoms to this state, about 23 will come down this path, 55 will go this path, 20 will go this path, and 2 will go that. So that is the kind of the problem with this approach, that we are sort of limited because of the branching ratio, right? So given this limitation, the question is, okay, what is the signal strength that we see in the current state of experiment that we are doing in the lab? So one of the first tests that we wanted to do is we wanted to try and understand what is the strength of absorption in this channel, in the 420 channel. Right? And when you are looking to do an absorption measurement for any atom, okay, what you need to know is the saturation intensity for that transition. Unfortunately, if you look in literature, okay, what you realize is that nobody has quoted the saturation intensity for this transition, either from theory or from experiment. So that was kind of the first measurement we wanted to do. That okay, if I want to answer this question, that what is the absorption strength in this channel, I would need to know what is the saturation intensity. So towards that end, okay, let me just go forward. Towards that end, we said, okay, we are going to shine some weak probe beam in the vapor cell and sort of record the absorption spectrum. And then we try to model this absorption spectrum and see what's the saturation intensity going to be. So you are potentially aware of this light matter interaction model, okay, where you can sort of model the light as interacting with some dipole, okay, and so there is a oscillating dipole, and so there is a polarization that happens in the medium, right? And so because the medium gets polarized, okay, there are two kind of categories. One is in the weak probe regime where the strength of the field, okay, the Rabi frequency of the probe beam is much smaller than the spontaneous decay rate of the excited element. So this is the level potentially at which every experiment happens, okay, in the weak probe regime. And so in general, for most of the experiments that we do in the lab, okay, typically we try to keep this Rabi frequency lesser than 6 megahertz. Why 6 megahertz? Because if you look at this energy level diagram here, here. So this energy level diagram, okay, these states, all of this have lifetimes which are on the order of 6 megahertz. So whatever light intensity I put in has to be smaller than the lifetime of that state. Then only I am able to satisfy this weak probe regime condition. Right? And so when we do that, what happens is that the vapor, okay, the atomic vapor in turn develops its own internal response to the light that is falling through it. And so this light that is creating these atomic dipoles, okay, we can sort of model this using the atomic electric susceptibility. Okay? And so if you look at the susceptibility curve, right, you have probably seen this thing. Okay, so for people who have sort of read this Griffith's book in electrodynamics, okay, there is a chapter where he talks about the overall polarizability of the medium using a classically damped harmonic oscillator, right? So this is the same model, right? We're talking about overall polarizability where you can see this quantity. This is the classical susceptibility. Right? This is called the Lorentz oscillator model. Right? And so the real part, okay, gives us what this gives us the dispersion, okay, the blue curve. This is the dispersion curve. And the imaginary part is what gives rise to the absorption, right? So if I send a light beam through a gas sample, I will usually see this structure, the red structure, okay? And through that, I can model the. So here's a quick overview of the experimental setup. I have a laser, I have some optics, I have a fabricator unit to monitor the spectrum of the laser, and then a part of the laser actually goes to the cell. There's a detector here, and it goes to some display unit oscilloscope, right? And so you can see this basically boils down to the very first slide that I showed you, that to build any kind of quantum sensor, you need a light source, you need a vapor cell, you need detector. Okay, you see these three key elements here. Of course, in order to monitor the light itself, I need various other sensors, but that's a different story, right? So at the heart of this, I have a vapor cell, I have the light source, I have the detector. Right? And so here's a quick overview of what kind of signal we see. So you see these yellow traces, okay? These yellow traces are actually coming from the fabricator interferometer. The blue trace that you see here, it comes from the absorption that you record in the atomic. And so what we do, we want to accurately model this such that I can recover this susceptibility. And from there, I can calculate what all parameters I want to, what I'm interested in. So here's an experimental data, just a quick snapshot, right? So these are actual experimental plots, and then we have fit them to the numerical model that we have created. And so you can see the residuals, how good the match is with respect to the different curves at different temperatures, right? And so we have posted these findings in this paper on the archive, right? And here's a quick experimental overview of what happens when you use a commercial vapor cell and you do these absorption measurements. Okay? This is what happens. With respect to the absorption measurements that we have done, right? For example, through this approach, right? So what was the motivation? Why are we interested in the absorption plot? Remember, I showed you one table where we had listed a whole bunch of quantum sensors, and we said that we are interested in getting optimal signal to noise ratio. That can happen if I know that this atomic quantum sensor has sufficient number of species inside it, right? So how do I know what is the atomic density inside my gas cell, right? So the only way I can, estimate that is doing this absorption spectroscopy. So you need to do this careful analysis, and from there, if you model things correctly, you can then say, okay, if I get a certain absorption curve at a certain temperature, what is the vapor pressure or what is the atomic number density at that? So this is why you're interested in. So when you do this measurement at different temperatures, so you can see as a function of temperature, okay, this vertical line here, this represents the phase transition temperature for rubidium. So rubidium is an interesting material, okay? It vaporizes directly to a gas, okay? It sublimes to a gas, even at body temperature, right? So if you can see, these are 312.45 Kelvin. So if you subtract 273 from this, okay, it's a temperature which is reasonably low. It's not very high, right? And so it has substantial vapor pressure even at room temperature. So what we did, we made a series of absorption measurements across various temperatures, and we tried to sort of map the number density, okay, against every absorption data we required. And so this blue dashed line that you see, okay, that's like an empirical relation that has been created by a group, okay, by studying various kinds of absorption plots. And so what it shows us is that our data is in very good agreement with that, empirical, data structure, right? So you can see that there's a very good agreement between temperature and number density through this empirical data class. And so what we then wanted to see is, okay, is this data, whatever we are measuring in the lab, is it consistent with other groups? So interestingly, there was a paper from one of the Chinese groups where they measured the vapor density from a completely different, process. They did not do absorption measurement. They did something else, and it was done at very high temperatures, right? But what you find is that our data and their data all along, okay, they are all falling on this empirical data line, right? So this shows that, okay, whatever we have measured is actually quite valid, because if these points were off, okay, they would not agree with the data from the Chinese group. So this paper is already published, okay, and this is what we have put up on the archive, and it is under review. So then, as I mentioned, okay, we have solved one part of the puzzle, which is knowing the local number density for a given wavelength, right? Now, what happens if we try and do the same measurement with some other wavelength? So we also went ahead and we tried to measure the absorption spectrum at 420 and trying to compare, okay, trying to compare the number density that you measured using 780 nanometers and the number density you get using 420 nanometers. And interestingly, okay, they all fall on the same line, which is good, which actually validates our measurement process, right? The theoretical model that we constructed to decipher the number density from this absorption measurement is actually validated because it works at two different wavelengths, okay, across various kinds of cells, right? So not only did we use the commercial cells, which are of very long length, we have also used these MEMS cells to do these measurements, and all these numbers actually fall on the same line, right? So now coming to the question of saturation intensity, right? So how do you define saturation intensity? Well, just to go back, okay, you have these various kinds of energy levels, and these energy levels, of course, are associated with different kind of photon energies. And so the question is, okay, how do you define the saturation intensity? It's basically that the intensity at which the population in the excited state reaches half its maximum possible values, right? So you all know that for a two-level system, okay, if I have a two-level system, and even if I put infinite amount of energy in the system, what at max I can get is 50-50 distribution of return. That is why you can get a laser using two-level system. The classic definition why I cannot build a laser out of a two-level system is because I cannot create a population inversion. Because no matter how hard I form the system, the best distribution is going to happen 50 excited. And so from that context, if you define the saturation intensity, it's basically the intensity such that the population in the excited state reaches half its maximum value, right? And so the question is, okay, I am interested in this 420 nanometer transition, but so far there is no conclusive measurement which tells me what this value is. And unless I know this value accurately, there are other measurements which will get affected. Okay, so what we wanted to do is, how do we create an experiment which can help us measure the saturation intensity of this transition? And so what we realize is that, yes, it is possible to do. So here's a quick math, okay, for those who are interested. I'm not going into details of this. But what we realize is that for the 420 transition, the theoretical value for the rubidium 87 isotope is this much, and for the rubidium 85 isotope is this much. Okay, so this is what comes from theory. Okay, after doing all the math, all the calculation, these are the two numbers we get. Okay, and these two numbers are not quoted so far in any literature. Okay, that is very interesting. So now the question is, okay, we get this, but then how do we validate whether this theory is correct or not? Right? So can we create an experiment to actually measure this? It seems that yes, we can. So what do we do? Okay. So once again, we go back to the same setup. Okay, but now instead of this infrared light at 780, we are passing the blue light, right? 420 is in the blue side of the visible range, right? So this is all 420 nanometer light. And so once again, you see the spectrum is very different, right? So you have the four Dopplers, and these are the fabric peaks, right? And so what you then do is, what you measure is as a function of this power, okay, what you do, you are plotting. So you can see within this big curve, there is this sharp series of peaks, right? And so if you zoom into that area, okay, if you zoom into this area or that area, okay, you will see that that sharp line represents a series of fine lines actually, okay? So these are called the hyperfine transitions of the atom, right? And so what we want to do is, we want to understand how those hyperfine transitions, how those lines that we are observing, how do they change if we put more and more power in the system? Remember, beyond a certain point, if you start putting more power, what is going to happen? It is going to lead to broadening. That is called saturation broadening. This is a well-known phenomena. It has been observed over the last 100 years. Okay, and so we take that idea and we try to measure, okay, this broadening, and then from the broadening, we try to sort of backtrace and see where I get an intercept. That is the value for the saturation intensity. Now, question is, this is an unknown method. Nobody has tried this earlier, and so we wanted to validate this. So what we did, we did a series of measurements on 780, which is a much more well-studied transition. And we saw that, yes, if you do this measurement at 780 using this, using this formalism, you can actually get back the saturation intensity for the 780 transition, right? And so we can prove that. So what you see here, you see that you have this power, okay, and then as a function of power, you are measuring the hyperfine coefficient, the hyperfine width of the transition, and then interestingly, okay, what it tells us is that the overall line shape that you measure, you have the natural line width, you have the power broadened line width, you have the transit time broadened line width, you have the residual line. And so what we want to do from this measurement is, we want to backtrace this fit, okay, and see where it hits the zero power line, okay. That is the saturation intensity line, right? And so when you do this, okay, what you realize is that the total line width is basically the natural line width times this interesting function 1 plus I by I set or B by B set, okay, plus the transit plus the residue, right? And so what we want to do is, we want to fit this to the value of PSAT, and from the curve we can get the value of residual, right? And so what we realize is that yes, the theoretical value of ISAT at 780 is 3.578, and the measured value, okay, that we measured from our own experiment is 3.57. So you see that the theory and measurement actually are agreeing very, very nicely. And so this validates our measurement protocol. So then once we are sort of satisfied that yes, this method is working for the known wavelength, which is at 780, then we go to 420. And so we do this measurement once again. So you see, when you zoom in these four regions, right, you get this series of hyperfine transitions. So you see there's a series of peaks here. You zoom this guy, you will get this. You go here, you will get this. You go here, you will get this, and this, and this, right? So you see, these are the all hyperfine transitions of the atom, right? And so what is interesting is that if you do the same trick for the 420 transition, okay, you can see that once again you get this linear kind of dependence on power. There's a gamma square linear dependence on power, and then you re-extract that, you look at the zero crossing, and then you can sort of determine where is the ISAT. And so for the theoretical saturation intensity for this 87 RB transition for the 420 nanometer is this much, okay, and from the measurement, okay, we get this. So you see, it's once again a very, very close match. So this perfectly validates our measurement that, okay, not only have we validated the protocol of the measurement because we have done this for 780, but now if we apply the same technique to an unknown wavelength for which people don't know saturation intensity, we can actually extract the saturation intensity. So theory and experiment values match quite well. And so here's this nice plot, which gives us a very good indicator that yes, everything is as per theory and everything is matching very well. So here's a quick snapshot of all the measurements that we have done, right? So this one you have done for 87 and this one for the 85, right? And so everything is matching pretty closely to the theoretical values and the experimental values. So this measurement scheme is now quite well established and valid. Right? And so the next thing that we wanted to do is we wanted to understand, okay, now that we know the saturation intensity, now that we know what is the number inside the cell, the next question that as a atomic clock builder is how well can we sort of understand this spectroscopy, right? So what do I mean by how well can we understand this spectroscopy? So essentially, when we excite any atom from the lower state to any excited state, the excitation happens because of certain hyperfine coupling coefficient, right? And so the question then is, okay, if we are doing everything correctly, we should be able to recover these hyperfine constants from the spectroscopy, right? And so we did this for 420. So once again, this is the generic expression, okay, for any hyperfine level. You see there are these coefficients A and B. And so our intention is actually to see how well we can match the A and B values for the 420 nanometer transition. And so when we do this, you can see, okay, this is a plot that is taken from this Glasser paper, very, very recent paper. Okay, they have access to the most sophisticated equipment. Okay, they are from Germany. Okay, they are a group in Germany. And so they created this plot, okay, where they showed their work and their error bar against published values. And this is where our work is, right? So measurement of A and B hyperfine coefficient also is in very good agreement to the other group's measurements, right? So this is one measurement, and then this is the other measurement. So it's very comparable, right? And so this is done with a much less sophisticated setup, right? So if you look at the work done by Glasser et al., they have access to a frequency comb which is stabilized to a GPS signal, and then they have done everything in sort of bits and pieces, and then created this, data constellation from which all these measurements are recorded. Our experiment is extremely simple, okay? We have the cell, we have the light, we scan the frequency, we get the spectrum, and that's it, right? End of story, right? And interestingly, if you look at the error bars, okay, they are comparable to what has been reported for the class of paper, okay, and sort of that sums up the discussions that I wanted to present before you. So, yeah,
Go back.
yeah, sure.
Right before. So here the error bars in the your work and the last two work.
So our work is at the very top. This guy, yeah.
Yeah, but there's not enough error bars really. It looks like the answers are actually because all the previous ones seem to be consistent with each other, right?
Mm-hmm.
The new one seems to say something because you see what I mean? Like the error bars are small and it looks like they're not.
So you mean on this error bar on this?
Yeah. Is it like how do I understand? How should I think about this?
So basically, what it means is that so when we do this measurement, okay, we okay. So here's the thing. Let me go back one slide. So
sorry, I'm also a little bit distracted with something.
no, it's fine. It's fine. So how do we do this A and B measurement, right? So as our group does not have access to these very sophisticated frequency measurement facilities, we cannot do an absolute frequency measurement, right? So we are limited because of our whatever our experimental limitation. We don't have access to frequency codes and stuff like that. So then what do? We say, okay, I cannot measure the absolute value of this transition, but what I can measure is the relative difference, right? And so what we do is we measure the relative difference in the position of these hyperfine lines as a function of the laser power. Okay, so so basically there is some reference number which comes from theory, right? Somebody has calculated the A and B coefficients from theory, and from that they have said, okay, this should be the energy level value for this transition. We don't have access to directly measure the transition. What we can do is we can measure between this and this difference we can measure. So using their established values of A and B, we say, okay, what should be the theoretical difference? And then we make a series of measurements, and then we look at the spread of those measurements, right? And then from the spread, okay, we build a histogram, we fit a Gaussian, we get an error, and then we normalize that with the number of measurements by 1 by root n standard. And so from that, okay, because we do a whole series of measurements, the standard error reduces by a lot, right? Because the number of measurements we make are extremely high, right? So that is why you see that the error bar on that, the red one, is relatively low. Okay. So what it shows us is that it is possible to get accurate measurement of this A and B hyperfine coefficient, even if you do not have the means to do a direct measurement of the energy. So the German group, okay, they have access to these fancy instruments. So they were actually able to measure directly, okay, what is the energy value at that? We don't have the frequency form. So we figured out a sort of different mechanism to say, okay, I don't have the frequency form, but can I still use my data and analyze and see whether I can recover the A and B information? That is what we are doing.
Yeah, no, that's what I understand. So, but what I'm not able to understand is normally all the measurements that are consistent should stay inside the error bars. But the one at the top doesn't seem to stay inside.
So now the question is, which error bar are you talking about? So here's the first measurement.
Essentially, all of them, right? All of them seem to be like inside each other's error intervals,
right?
But the top one doesn't seem to be. So I'm just trying to see, is there some systematic?
No. I don't think so. I mean, so for example, are you talking about the size of the data point not being within the vertical line? Is that something you're worried about? Or?
We can discuss afterwards.
Okay.
I'll ask you later.
Sure. No. So these are the two measurements that we did. I'm sorry, let me go back. Yeah, so these are the two A and B measurements we did, and I just wanted to sort of brief you on the future directions. So one of the things that we are now going to do is all these measurements so far were done in a normal environment, right? But then Earth's magnetic field itself can be sort of an external perturbation on these measurements. And so what we are trying to do now is we are trying to create a shield for the Earth's magnetic field and then redo these measurements at a better precision, right? And hopefully that will give us some more insight on how well we have been doing these measurements, right? And then the other thing what we are interested to do is we have this laser which is sort of probing the transition at 420, and we want to sort of stabilize the transition at 420 and see how strongly stabilized that laser is, right? With respect to time, right? And then in the near future, hopefully, the aim is to actually see if we can sort of put everything in a small box and create a portable atomic clock technology prototype at 420. Right? And so that sort of brings me to the end of my talk. And so here's a picture of the two gentlemen who were responsible for all these measurements. So they were also assisted by Shankar, who is an intern, Urvisha is an intern, Elil, who was an intern, now is in NTU, Chandan, who was an intern, now is in TI for Hyderabad. And this MEM cell that I showed you at the very beginning of the talk, that is actually coming from the RIOS lab in ISRO, and these are the collaborators from the RIOS lab. So I'm also thankful to ISRO Respond program for the funding. And of course, there are other infrastructure in the lab where it's funded by our own institute and the Center for Atomic Molecular Sciences and Technology. Right? So this is Shumai, this is Shivam, and that's my extended group, that's my lab, right? So you have, Elaine is right now at NTU, Chandan is right now at TI for Hyderabad, and then this is Himanshu, he's right now at ICFO, Barcelona, and this guy, he got this Indo-Japan Lotus Fellowship. Right now, he's in Okinawa on clock project itself. So so this is Ashok and Sumit, and so this is kind of the group we have right now. And I end up with a nice picture of our campus. This is how the campus looks. So all of you are welcome to visit our campus. And of course, if anybody is interested in some project or internship in communication or in clocks, I mean, of course, we will be happy to host them. We have the funding to the National Quantum Mission as well. So anybody interested in semester internships, semester projects, I mean, you are welcome. Okay. Yeah, so that's it.